My name is Dmitry Sagatelyan. I'm a CLA LabVIEW champion and a regular presenter at an every week CLA Summit in San Francisco Bay Area LabVIEW user group. Coming from a computer science and software engineering background, I'm quite passionate about bringing contemporary software engineering methods and practices to the LabVIEW community. And my main entry areas of interest include after programming and using Agile design principles to design better LabVIEW architecture and code. 10 years ago, I quit my last full-time job and started Arthur Technologies. And I've been using solid design principles pretty much all the time since then. And using those principles helped me to consistently deliver scalable and lean customer solutions, which is a good thing. But as we know, every good thing comes with a price. So I found myself lately running out of architectural challenges. And if somebody wants to talk to me about the problems and challenges they face on their projects, I will be happy to learn about that. Now, having said that, let's get to the topic. It corresponds closely to what Sarah was talking about yesterday and John was talking about now. And also, I didn't attend Chris's presentation. I think some of the points he made, I would also make here, but the wording would be different. The topic is the same, the wording are different, so you need to kind of translate that part. So these are the two must-read books for every architect in this room. Who read the 2003 book? And I expected more people. Who bought this book? That would be the right question. Who bought this book? Oh, well, start reading it. This book is hard. Let me compare these two. The first book is focused on solid and package design principles, which work at the module and component level. It is quite hard to read for LabVIEW people because it has plenty of C++ examples and you need to go through them to understand the concepts. It is hard to digest because of abundance of novel concepts and dense content. And you may read it as a reference book by topic, by chapter. That's a good part in it. I found myself coming again and again to different chapters, and that was really helpful. The second book is focused on the architectural layer. It requires prior understanding of solid and packaging principles, so you need to read this book first. It is very easy to read because it has 0 C++ examples. There's only one example with PDP assembler, but you don't have to read it. And it is hard to digest because, in my opinion, the text is so generic that it's very hard to extract actionable items you can use on your project. That was the main difficulty for me. And with this book, you must read the entire book cover to cover to make sense of it. But once you do it, the picture in your head, the bulb in your head will light up because it explains how all the packaging and solid principles came into being and why they are the way they are. I read the second book like 4 times in 2 years. The last time while working on this slide, and I put a lot of quotes from the book with page numbers, to make it easier for you to relate the contents of the book. So even when you decide to buy and read this book, you can download the presentation, preferably in PowerPoint format, and go through the presented notes first. It will give you like a short review of what is happening here. Uncle Bob is a very outspoken person, and one of the reasons, if you don't want to learn about clean architecture, is to just skim the quotes you can use in your presentations and design review in meetings to justify your position. So the first one, have you experienced the impedance of bad code and rotten design? Everybody did. But to word it in this way, it requires some talent. The word architecture conjures vision of power and mystery. When we think of a software architect, we think of someone who has power and who commands respect. Aren't we all? That's why we're architects. I like this one. The dilemma for software developers is that business managers are not equipped to evaluate the importance of architecture. That's why software developers were hired to do it. Therefore, it is the responsibility of the software development team to assert the importance of architecture over the urgency of features. That's our main job. Our managers want the product to be delivered, full features on time, but we see a problem and we must promote the importance of architecture. And the last one was relating to his experience in the past. This was a startup. We worked 70 to 80 hours per week. We had the vision, we had the motivation, we had the will, we had the energy, we had the expertise, we had the equity, we had dreams of being millionaires. We were full of shit. So, just for skimming for this thing, it makes sense to have the book. And there is an electronic format of this book, but it doesn't have pages as the printed version. And I can show you later what it is. Signature of a mess. In the first chapters of the book, Uncle Bob kind of illustrates what's the price of not having a proper architecture on a project. This is real life data on a real life project, a market-leading software product. They don't mention his name, but I won't be surprised if this is about the Netscape browser that died prematurely, I think in late 90s. So it has 8 major releases, and the first plot shows the size of code base in 1,000 lines. And we see that it grows faster and then plateaus. And one of the possible explanations is that it is so good and implements all the features the customer wants that there is no need to add anything. That's a possible. The second plot shows the headcount and the engineering staff for those same 8 major releases. It grows exponentially. So what an optimist would do, he would say, okay, the company is successful, they got a lot of money, and they're investing in related products to penetrate markets even deeper, right? Otherwise, why would the staff grow that fast? But the third data set explains it all. The cost of adding a line of code as a function of major release also increases exponentially. This is not sustainable situation. The company would go belly up. Because to fix an error or to add some new feature, you put 20 times more money and resources into a line of code. And why this happened to the product? Because it didn't have a proper architecture. It didn't support easily changing the code to the new requirements. Probably it was, well, I don't have to say properly, it was designed by a very small team. Well, no, okay. It was designed by a small team. As we can see, there was like 20 or 30 people in the beginning, and they wrote 3 million lines of code. The line of code was inexpensive, but as requirements changed, it took more and more people, and they became less and less productive. So that's the importance of a good architecture. What is for future-proofing? The topic is future-proofing. This is a Wikipedia version. Future-proofing is the process of anticipating the future and developing methods of minimizing the effects of shocks and stresses of future events. It relates to any domain. If you look at the first Uncle Bob's book, I took out 3 snippets. The first observation is we live in a world of changing requirements. The second one, requirements change in ways that the initial design did not anticipate. And our goal is to make sure that our software can survive those changes. So given those quotes, I would say that the main purpose of using Agile design technology is to future-proof your designs and code. So this topic is, I think, most relevant to our summit today. Software has 2 separate and distinct values stakeholders. It is behavior and structure. Behavior is defined by the requirements, and the software team has very little say in this matter. You are handed the requirements by marketing or by customer, and you have to implement it one way or another. The structure supports implementing requirements. But structure has very little effect on behavior because you're not allowed as software developer to change requirements. Instead, structure determines the cost of implementing and maintaining the system. And the system with a bad structure, as we saw in the prior example, can work really nicely and be a market leader, but it will be very hard and expensive to maintain. And this software structure is often called architecture. This is our main responsibility as architects. I tried to find a good definition of what a software architecture is, and the closest one was by Grady Bush, the guy behind UML. Architecture represents the significant design decisions that shape a system where significant is measured by cost of change. This is the key part of the definition, cost of change. The more expensive the change is, the more important it is. Uncle Bob kind of expands on this and says that the architecture of a software system is the shape given to that system by those who build it. The purpose of that shape is to facilitate the development, deployment, operation, and maintenance of the software system contained within it. And if you think that's too long, you can use the last one by Martin Fowler. Architecture is about the important stuff, whatever that is. So we all know what architecture is, but it's very hard to word it properly. So on the prior slide, we can say that the goal of software architecture is to minimize the human resources required to build and maintain the required system. That's the goal. And since the maintenance phase is the longest phase in the life cycle of the product, pay attention to architecture. The architecture of a system, all these are quotes from the book, from the second book. If you don't see a number, reference, just page of the second book. The architecture of a system has very little bearing on whether that system works. There are many systems out there with terrible architecture that work just fine. Their trouble occurs in deployment, maintenance, and ongoing development. The way to keep software soft is to leave as many options as possible open for as long as possible. And that includes deciding on the framework you're using, on the database you're using, and whether to build a desktop interface or a web-based interface for the system. Those are details. They don't really matter to the business logic of your application. And if you delay the decision, you will have more information later on on which of the framework or technologies to use later. That will save you a lot of time. If you think good architecture is expensive, try better. Many of us probably learned it the hard way. So, what makes a software architect? What are we as a group? I would say there are 4 traits. First, we are tech leads. We interface with other teams on the project, marketing, management, and the customer. We contribute code. An architect who is not contributing code is not an architect, even on a large system. You need to be able to eat your output because it's the only way to get real feedback on what you're doing in the project. And the scope of your effort is the entire software system. Everybody agree so far? Yeah. Good. Now there are 2 archetypes of software architects. The first one is depicted by the architect from the Matrix Reloaded. And these guys, this type of guys, they make all important decisions on the project, and they need to make them early on so that they can hand off the work to the team members. The second one is kind of a Sherpa, a mountaineer guy. They watch out for the team. They make the system-wide decisions, and they're constantly looking for a curious problem and try to find solutions for them. They don't make all the decisions. They're just looking at how to safely navigate you from point A to point B. The matrix architect is the most qualified on the team, and he needs to walk on water. Otherwise, the project is doomed if the architects make decisions. On the other side, the Sherpa guy mentors and guides the development team. And matrix architect is becoming an architectural bottleneck because he makes all the decisions and we have limited resources in our brain, while the Sherpa type delegates decisions making to qualified developers because he mentors and guides them. And also if something happens with the Sherpa, one of the developers can fit with his shoes and continue leading the project. So the question for everybody is, where do you stand as a software architect on the scale of 0 to 10? In my consulting activities, I would say I tend to be on the left part for various reasons. One of them is my customers don't pay me for mentoring the team as the main purpose of getting me on board. I have to deliver the project. But while I was in my other full-time job, I did a lot of mentoring and guidance, so I kind of span both of the roles. And you can read about those architect types in this really nice little piece by Martin Fowler. Just follow the link. It's a fun reading. So let's get to the nitty-gritty. This is the big picture, in my view, of Agile software design. First, we have the Agile philosophy. That's the all-seeing eye on the top of the pyramid, which I skimmed out of a dollar bill. Then there is a single architectural level dependency rule that rules them all. Then comes the package design principles, which are described in the first book and apply at component level. Solid principle at the class and library level, design patterns, and the code. The first 5 are programming language agnostic. You can talk to a C++ or Java programmer and understand each other until they start showing them how you use their code. So it makes sense, I think, to invest in these 5 top level things because it will make you a better developer and architect, regardless of what platform you're using for the development.
So, a brief review of what I think the Agile software design philosophy is. I already read that quote. So to translate it, I would say that you need to make your code as good as it is needed at the moment. Don't try to anticipate changes in requirements and put in extra plumbing that would support those changes. In most cases, they would end up as dev code and weight your system down. And second one, refactor your code as requirements change, not before they're not. It's very hard to get changes in requirements for various reasons, and your strategy should be not trying to anticipate the change, but in shaping your code so it can easily be refactored later. So you can say that Agile philosophy is building your code so that it can be consistently or continuously refactored later on. Solid principles, package design principles, I won't talk about them. There were enough presentations before. They're related to each other. You see the blue arrows. But that's pretty much my last mentioning of those principles. And now the clean architecture. This is the diagram from the book. Here you have 4 architectural layers. Enterprise business rules is the innermost yellow. Application business rule is around the entities. Interface adapters and frameworks in red. This is what Uncle Bob put in his book, but he said that if you need more layers, you are welcome to introduce them. And there are similar works by different authors that were done over like between 2000 and 2010 that have like up to 7 layers. So it's up to you to figure out what you want to emphasize in your architecture. And there is a single rule that rules them all, the dependency rule. Source code dependencies might point only inward toward higher level policies. So the black arrows depict the dependency rule. What this really means is that your use cases should never make calls to the framework level and should never use any type that from the framework level. This way, they are decoupled from the frameworks you're using. And if you build your project this way, they become independent of the frameworks you use, independent of the UI implementation, and independent of the database you use as persistent storage. And they're also inherently testable because the 2 inner circles, the use cases and entities, which represent most of the value of the system, as John mentioned before in the presentation, they don't need the frameworks and databases and other stuff to be deployed in order to unit test them. So they are inherently testable. This is another way to show you the diagram. Yeah, and these lines between the circles are architectural boundary. Another way to show this division in layers is to split it like this. I don't understand why I don't have a mouse here. Is this better? Yeah, you see. So what you have is double lines are architectural boundaries. These are components. And what you have is your entities. You have your entities, you have your use case interactors, you have the UR layer, controllers, presenters, and then you have the database and the views, and the framework is somewhere here. what does a boundary crossing mean at runtime? It's as simple as directly calling a VI from the inner circle, or sending a message, or triggering an event, or generating a data structure from defined by the inner circle and pushing it there via message or call. And the red arrows depict the flow of control. Your events, user interactions start at the controller, or this may be the data acquisition system. Then the data is passed to the use case interactor, which implements the use case and orchestrates all the business logic. Interactor may access the database, fetch some data, and make calls to the business entities, which return results that are returned by the interactor to the presenter to be displayed on the UI. And then the presenter generates the updated view, which belongs to the previous plan. So this is the flow of control. It goes like that. And you see that in case of controller, it crosses the boundary in the right direction, in the direction of dependency. And in case of presenter, it crosses it in the opposite direction. So if use case interactor directly calls a method from presenter, it violates the dependency rule. And this is one of the things we need to learn to do as architects, how to insulate us from this kind of thing. The red arrows show you the allowed dependency direction. So the call goes from here to here, but dependency should go from here to here. You got a problem. We need to address it. And I'll talk about this right now. So how do we cross the boundary? You have a use case interactor that implements a use case, and it needs access to database. So what you do, you use dependency inversion principle in your use case implementation. The interactor defines the dependency interface that has all the methods it needs all on the database. And at the framework level, you create a data access object class that implements this interface. So the use case code calls the API, and the database does its job and passes results back, and you are decoupled from the database. That's what it means. It's just plain and simple dependency inversion. A more complex case is the two-way boundary. Here we see that the controller can call the interactor directly, but interactor cannot call the presenter directly. So what you do is you define an output interface in use case implementation, and the presenter implements it. This way you comply with the dependency rule, but your controller may be tightly coupled to the use case, and controllers sometimes, well, in most cases will have like large amount of code that is variable, and you may want to reduce it with different use cases or on different applications. So in that case, you do another trick, and your use case defines the input interface, which it implements, and controllers call into that interface. This is the two-way boundary crossing, plain and simple. Policy in detail, these are important topics. Policy embodies all business rules and procedures of the system. And policy constitutes the true value of the system. And details allow humans and the surrounding world to communicate to the policy. That's its sole purpose. The business logic is in the policy, and the rest is unimportant. Whether you talk to your banking system through a web UI or go to the bank and talk to like a regular desktop interface. And our goal as architects is to clearly separate policy from detail. This is what John, I think, was talking about in his presentation too. So let's talk a little bit about those layers, architectural layers. Business rules
two types of business rules. First, the critical business rules. These are enterprise-specific or domain-specific. For example, in case of tax preparation software, these are the federal and state tax forms. They exist independent of whether you do taxes using TurboTax or do it by hand filling the form. They exist outside the software house, and our goal is to automate filing taxes, and for this purpose, the software developers, the software team defines use cases which orchestrate how you fill in the individual tax form, and these are the use cases. And the use cases orchestrate how the user of the software interacts with domain-specific entities. Interfaces and adapters, you can see two words, controllers and presenters, which means clean architecture is based on some sort of monolith control paradigm. And in this case, it is like an MVP, model view presenter flavor. I'll talk about this later. And from my experience, all actors, worker loops, message handlers, and event generation should be confined to this layer. Your business rule should not be polluted by event handling. That's my personal take. The role of gateways is to translate data structures that are supplied by the frameworks and by the lower layer into data structures that are consumed by business rules, the yellow and the red layers. That's their main function. And they help you, doing that, they help you to decouple use cases from being statically dependent on the frameworks that you are using. So there is a really important design pattern. It's called a humble object that is used all over the clean architecture. And the purpose of, who knows what a humble object pattern is? Okay, I need to get some details on this. So, for example, you're designing an UI and you want to unit test it. It is really hard to automate unit testing a UI. And it has some business logic in it, the UI workflow, how the UI flows. So you want to be, what you do, you separate your UI component into two components. One is the presenter that does not render the interface, but implements all the business logic. And it is easy to automate unit testing it, because you don't have a UI that you need to second guess what is going on. And you have the humble view, the blue thing on the bottom, that just renders the data structure passed from presenter to our display drivers. These data structures, Uncle Bob calls them view model. They may be a set of strings for each control and for each control on the front panel, and all the tabs for that control. So what your humble view does, it just goes through the structure and displays those strings. It doesn't do any formatting, any rank checking, anything like that. It's given the data structure, it just renders it. So it really doesn't matter for you whether you implement a desktop UI or a web-based UI, because this object is small. You still need to make sure it works, but it's very simple and it takes less time to debug it. So you will see the humble object pattern in many cases in the clean architecture. The most controversial thing is the frameworks and drivers layer. It specifically contains the devices, the web, the UI, the database, and external interface.
And what Uncle Bob says is that a good architecture emphasizes use cases and allows deferring decisions about database, UIs, IO devices, and frameworks until much later in the project, and makes it easy to change your mind about those decisions. And this happens because you protect your business code from databases, from frameworks, etc. It's easy to say, but the question is how you decouple your code, how you protect it from the framework. So I'll talk about this a little bit later. I got 17 minutes, I think we're good on time. Here is an example of a clean architecture. Uncle Bob not just writes books, he does training video with his team. And you can go to his website and look at the videos and buy them and watch them, a lot of them. So this is an example how they architected the video sale app for their training. You have 4 actors: author, administrator, purchaser, and viewer. And each of those round things is a use case. So, I can zoom on this, probably. Yeah. Is this better? Okay. So what an author can do, it's a use case for submitting a video, submitting an exam, and submitting a video description. Administrator can add a new series, publish videos in a series, remove a video, and set licensing price. Viewer can view the catalog as a viewer, stream a video, download a video, and a purchaser for like large accounts can do his own. So you have 4 actors. Do not confuse them with actor programming. This is UML actors. And it doesn't use speed. So the structure for implementing it is on the diagram. Each box represents a component. And the code is organized on a per use case basis. And it has the interactors which implement the use cases, has individual controllers for and presenters for each use case, and view. And so it does for each of the actors. And it separates the code, clearly separates it into the 4 layers. Red arrows again is the flow of control. It always goes from controllers to use cases to presenters and then generating views. And that's pretty much it. That's a clean architecture for this project. So what you do, you as an architect, you draw architectural boundaries, the double lines, and you organize your code on a per use case basis. In a large application, each component may be developed by one developer or a small team. On a smaller application, and they're independently developed because you have well-defined APIs. But on a smaller application, you can group the use cases and handle them to different teams. And as a result, they are independently testable, buildable, and deployable. And when you need to change a certain use case, the changes don't propagate across the architectural boundaries. So that's pretty much it. In his book, Uncle Bob also talks about a possible fifth layer, which is the gray one. And he says that tests are pretty much part of the system, even if developers don't think that is the case. Always treat your test, whether it's unit test, integration test, behavioral test, acceptance test, or other types of tests, as part of the system. This way you can make them less fragile because For example, unit tests are so detailed that any change in the code that was generated by changes in requirement would break many tests. And the second entity, this is a pretty big thing here because the amount of tests may double this or triple the size of the system. And the second one is the main component, the main VI that actually starts the system, brings it up, runs it, and queues it down. It contains all the system-specific knowledge in the code, and the rest of the code is supposedly reusable. So, database is a detail. I told you how to decouple from it, simple dependency inversion. But by database, in this book, what is relevant is it is the persistent storage. So if you're not using database, but using INI files to store configuration, that's a database in the context of this book. So it includes the bona fide databases like Oracle, MySQL. It includes the file system if you store results in a file. And it includes the file storage format. And as an architect, you would be really good if you understand the importance of decoupling your business code from these entities. Because then you can switch file formats based on requirements from your marketing team with minimal changes. What the book says, essentially, well, I'll skip on this one. The UI is a detail. I showed you the humble view thing. And if you implement presenters, you implement the bulk of the business logic of the UI and event handling. And later on, you can choose a specific web technology that is appropriate for the application. So that's why it is a detail. If you defer this decision, you're in a better position to make the right choice without reworking lots of code that you put in early on. In LabVIEW, we have a problem in this respect because LabVIEW resists splitting UIs into presenters, controllers, and view. Each control and indicator implements parts of those three things. So we need to make a decision whether we want to split it and how we do it. And by the way, those controls and indicators in the older days, I think they were a compelling reason for people to switch to using LabVIEW for better prototyping, because the UIs were really easy to make, but as you get deeper into software engineering and architectures, this becomes like an obstacle, because you make an effort to separate those things. Okay. And the way you separate controllers from views and from presenters, one of the good ways I use this is a message broker. I think I presented it back in 2016 at the summit. You may want to review it. So what it essentially does is a topic-based publish-subscribe mechanism. And in my reduced libraries, I use it for routing messages between apps or SKUs. And what the message broker approach allows you, it allows you to decouple publishers and subscribers from each other. It allows you to decouple publishers from topics. You don't need to instantiate a publisher in order for a subscriber to subscribe. Subscriptions are done by message broker. It supports one-to-one, one-to-m, one-to-many, and many-to-many message routing schemes, which is important when you scale architecture. Objects may publish and subscribe to multiple topics. And as I said, it removes constraints of object classification order, which is a really important thing in complex systems. Sometimes it is so convoluted that it is not possible to instantiate it in the right direction, in the right sequence to establish all the connections. So the last one
Frameworks are detailed. This is probably the more controversial one. And I didn't hear Chris's presentation yesterday. It was based on John's remark. I think he was saying the same thing. Frameworks are detailed. Architecture should not be supplied by frameworks. Frameworks are tools to be used, not architectures to be conformed to. If your architecture is based on frameworks, then it cannot be based on your use cases. In other words, if you mindlessly use after framework, I'm not saying you should use it, then your architecture is dictated by after framework. And the question is, how do we protect our applications from framework? This is one of the things I want to kind of analyze in my future research activity. I think I know how to do it, but I'm not sure because I never tried it in practice. Okay, we got 7 minutes. I'll skip this slide. Does anybody know what a framework is in software engineering? Okay, one person. Let me go for this. So this is from Wikipedia, the software framework topic. And according to this slide, it is a framework implements inversion of control. It commands the flow and control in your application, such as after framework. It is extensible. There are extension points. That is the after object. And it has non-modifiable code that you cannot edit. Again, this is the after object. So after framework is definitely a framework, but many frameworks on the prior slide that we use to hold framework, like I think DQMH and the messenger library and some other stuff, they're not frameworks, they're reuse libraries, I think. Yes, sir.
It strikes me that saying you should defend your code against the frameworks would be almost equivalent to saying we should make code that is defended against data flow.
No.
How do the frameworks, the ones that are mimicking language level features that are controlling your flow of control, how do those differ from the choice of language? I mean, if you've chosen a programming language, you've almost inherently chosen a particular architectural style. And if you're saying we need to be defending against architectures, that's almost saying you need to be able to defend your code against your choice of language, which I think is a contradiction.
That's not possible.
I agree. I'm contending it's not possible to defend against the architectures that your frameworks are dictating either.
I can show you how you can do it. Next slide. I think you can do it this way. I never tried. Because I'm not using a framework. This is a...
Can I add something? So one of the thoughts I've had lately is to write my code so that I have an object that does something and then wrap it in an actor or in the DQMH then to send the messages, and then it is somewhat decoupled from how the messages get in and out of. Does that kind of make sense?
That is a good implementation. I don't think that constitutes a defense.
Well, I mean, it's independent because I can take that object that represents my business logic and I can put it in an actor or I can put it in a DQMH module. It doesn't matter.
But if that object is itself an asynchronous thing that has internal components to itself that are asynchronous and reactive, then it's got actors inside of it and you're fundamentally welded to its behavior. Whether that's DQMH, whether that's AF, or any other framework, if you're writing with event structures and message passing, then any change that you're using as a reactive programming model, I honestly don't see what you even mean by separating those two concerns.
I'll show you.
Okay.
So this is what you do with actor framework. You have the actor class in the framework, and you create your actor class, and it becomes an actor only once you inherit from the actor class in the framework. This is a blatant violation of dependency rules. your business logic starts depending on the framework. So how can you get around this? This is just something, a way to do it. You create an actor in like the presenter or controller layer, then instead of inheriting from the actor, it has your business case object. It has, and it calls it in the block layer. This specific way doesn't work because an actor, the actor framework actor cannot implement multiple actors. It doesn't work this way. So this is just an idea, but this is a way you might be able to implement it. You create an actor interface that decouples your code from the actor framework. And you create my actor for each of your use cases. And your actor has the AF actor and the use case and orchestrates their use.
All right, but my use case, is that a class?
Yeah, it's a class.
So it's still inheriting from LabVIEW object.
Yes.
So it's already chosen an architecture.
It's chosen a language.
That's what I'm trying to get you to differentiate. Is
LabVIEW object does not dictate an architecture. Actor class does. All classes inherit from LabVIEW object. Okay, Jeremy is showing that it's time. And I was promised another 5 minutes because we started late.
That's true.
Should we listen to Ellen or should I continue with like the 3 slides I have? Okay, you can vote it down. Okay, we can discuss later. If we have time, we can like get together in the room. So the other thing is whether using a message broker like I do creates the same problems. And I think it doesn't because I don't have to inherit from the actor class because I don't have actor classes in my reuse library. I have a template like PKMH and I create the template from the template every time I need an actor. So that's the short version. So my library uses a message broker, which I think resides in a message broker which has an interface and an implementation. The interface resides in the actor layer because in my view, all of the handling should belong there. Implementation resides in the framework layer, and since all event handling goes here, logging, which is also supported by my reuse library, also belongs to this layer. These are the components, my reusable components. One other thing that my reuse library does is error handling. I reported on this at NL Week and here at the Summit. My errors are objects that you can implement, and they can be passed using existing error files. So they are objects. And this I think, should be considered as an extension of G, because all the layers should be able to generate errors. Your use cases and entities would be coupled to error handling, and it cannot be put into this layer. So my thinking is that you need to introduce an extra layer, which is G extensions, and you should put only really stable classes out here. And in this way, as Steven mentioned, you have the G language, we always depend on the G language. So, slow and dirty, probably last, well, I have 3 more slides. So, multiple times a year, I'm tempted to do a quick and dirty thing to deliver a feature really quickly.
And all of those times I regret it later, maybe the next day, maybe 2 weeks from there, maybe 2 months. And what I have to do, what happens is somebody comes up and says, well, I need that feature, and it does not work well with my quick and dirty implementation. So I have to take out the old code, do the proper implementation, break all the colors, retest everything, and put in the new one. This is not quick and dirty, this is slow and dirty. Just call it slow and dirty. If your management wants you to do something quick and dirty, tell them it will be slow and dirty then. So Jason Gorman has a nice presentation on this, and this is like one of the slides on this presentation. One of the illusions the software development team and project management has is that we need to deliver now, we need to get our foothold in the market, and then we'll sit down and redesign our product in the clean way. This is a myth. They would never allow to do it on the entire project because the priority is strict. You get competitors breathing down your neck, and your marketing says, we need the next 3 killer features, do it now. And you say, well, my architecture doesn't support it. And it's your fault because you actually agreed to do things quick, so quick and dirty. This is for products. Oops. For startups, it's also relevant for a different reason. The lifetime of your software in startups is minimal, and its value in delivering critical knowledge. But prototype designs change at a rapid rate, and in order to redo your software that controls the prototype, you need to add features which is cost prohibitive if you do quick and dirty stuff. So as an architect in a startup, you need to insulate yourself from quick and dirty, otherwise your team will be really angry at your doing. So the final quote is, the only way to go fast is to go well. Don't fall for the quick and dirty scam. Summary. I said that extracting actionable items from this book is really hard. I think Alan Smith agreed to me about that when we were sitting at GDevCon this year. So I took the effort and put out the actionable items that you may want to apply when you start practicing clean architecture approach. First of all, clean architecture is a mindset. You don't need to put any plumbing up front. You just need to start thinking that way. No initial infrastructure. Typical LabVIEW projects start small with few formal requirements. So what I would do is use solid principles, the first step, to design and implement classes, and leave as many options open as possible for as long as possible. Don't decide on the framework before you implement the business logic. You'll get a better understanding of your project if you implement first and unit testing first. As application grows, start using package design principles to group classes into cohesive components. And once your use cases shape up, group your components into use cases, and always adhere to the dependencies. Jeremy is nervous. So there are 2 more slides. How do you create architectural boundaries? Yeah, very easy. If you run your code from LabVIEW IDE or create a single executable, these boundaries do not have physical manifestation. What you do instead is you organize your project. Oops. My bad. You organize your project in a way, you create folders, virtual folders over there for each of the architectural layers. And you create put classes in appropriate layers and so on and so on. That is an easy thing. And if you obey certain naming conventions,
conventions, then you can create a VI test, a VI analyzer test that checks that lower level components don't call into top level components. Business logic doesn't call into lower level. So this is a matter of organizing stuff. Once you get into plugins and PPLs and components, it becomes more difficult. Use dependency inversion principle, and remember that it is very expensive to introduce an architectural boundary out of the pattern. But on the other hand, we don't force to introduce them in every place because, again, it's expensive. And these are the differences. So you can get to the good stuff. Then my to-do list. After this presentation, I have three action items. I have this ArtLib reuse library, and I want to rearrange the components, how I deploy it according to the architectural level. It will require some refactoring, especially for error handling. I also want to figure out whether and why Echo framework would create obstacles for doing a clean architecture on your projects. And I want to refactor my reuse libraries to the native G interfaces that we are supposedly getting in LabVIEW 2020. And that's it.